Hi there everyone, my name is Afan, and today I'm going to start a new topic, something that I've been wanting to start for a while now on this channel, and so today is the day where we started. So the topic I want to start is really the basis of integration. So integration is the other half of calculus. So if you're watching this video, I'm hoping that you have done some differential calculus, and you know how to take derivatives, and you know all the ins and outs of differential calculus. So naturally the next step that you take is integral calculus. So today I'm not going to go right into integral calculus, but I'll start talking about antiderivatives. So what exactly are antiderivatives, right? So that's what I wanted to address today, and maybe in the next video I'll cover some examples of antiderivatives. So an antiderivative is something we call an integral. So you probably don't know what an integral is right now, what's the purpose of it. So I'll just give you a sneak peek of what we're going to do with integrals, is that if I had a graph, so for example my x and my y, and I had some continuous function, right? That's a continuous function. And I had two bounds, so I'll call this A and I'll call this B, alright? And I wanted to know the area under the curve right here. So I wanted to know this area down there. How would I figure that out? Well, believe it or not, calculus is the job for this, and we do the opposite of differentiating. We take an antiderivative, we take an integral. So that's really the point of integral calculus, is finding areas under curves, or just areas in general. So you'll notice that a lot of the formulas we have for areas are actually going to come right out of integral calculus. So it's going to be some time before we get there, but I'll just give you a heads up that that's where we're going to. So antiderivatives, let's just stick with that topic for today. So we all know that if we had a function, right, y equals x squared, right, we all know that if I did dy dx, it would just be equal to 2x, right? I lower the power by 1, and I multiply by the power up there, right? Simple. We're used to doing that. So the point of antiderivatives is that what if you weren't given the function, but you were given, in a sense, the derivative, right? What would the antiderivative be? What would be the opposite of differentiating? So we don't get questions like this. This is not how it's going to look like, where you'll have dy dx equals x squared and they want you to find y. That's not how it's going to look like. How it's going to look like is this. So there's going to be a symbol that looks like that. Very cool looking symbol in my opinion, but that's the process of integration. So this right here we call sum. And you'll understand why we call it that soon, but for now that's the symbol we use. And what it'll look like is you'll have this symbol, and you'll have a function, let's say f of x, and then you'll have dx, right? That's exactly how it'll look like, and that's the problems that we are going to solve. So let's go ahead and derive a general antiderivative, alright? So what if we had the integral of some function to the power of n, alright? What if I wanted to find the antiderivative of just some power to, or just some function to the power of n, right? That's all we're doing. So the formula for this is you keep your x the same, you add 1 to the power. See, it's the opposite of differentiation, right? In differentiation, we would lower the power by 1 and then multiply by that power, right? So the opposite of differentiating is you add 1 to the power and you divide by whatever you added. So I added 1 to the power, and I divide by that number down there. So this is the process of anti-differentiating a basic function, like any polynomial function like this, right? X to the n, you would add 1 to the power, and then you would divide by n plus 1. And there's something you need to add. Something you need to add that I really stress, and every single other teacher will stress in integration. You have to add a plus c. So you're like, whoa, why do I add a plus c? Well, what does the plus c mean? Well, c just means constant, right? So the reason we add this constant is, think back to differentiation, right? When you take the derivative of a constant, what happens to it? it just disappears, right? It's gone. It's like it never existed, right? When you take the derivative of a constant. So if we're doing the opposite of differentiating, we have to bring back that constant. That constant that that disappeared when we differentiated, we need to bring back that constant. And thus, whenever we do a problem, any integral, indefinite integral, I'll explain what that is in the future, but anytime you do an integral, add that plus c. For now that you're watching these videos, if you're doing an integral, add the plus c right now. All the examples that we'll do, please add the plus c, because again, when you differentiate, constants disappear. But if you're anti-differentiating, you need to bring back that constant and can't just stay gone, right? You're going backwards, so you need to add it back on. So let's do an example. Okay, what if I had the integral, indefinite integral? I'll explain what that means again in the future videos. So let's say I had the indefinite integral of x to the 4 dx. Alright? I wanted you to find the integral of that. Well, why don't we use the formula we just derived and the formula that we just found to get the integral? So we add 1 to the power. So what's 4 plus 1? That's 5. And you divide by that same number, 5. And again, add the plus c, alright? And that is your integral, alright? One other thing I'll just show is this right here, we call the function, alright? And this right here, the integral that we found, we call the primitive. So it's just a capital F and then x, so there we go. So this is the function, alright, and whenever we find it, we can just say this is f of x, but capital F, alright? And a cool thing about checking your work in integral calculus is, how can I make sure I did this correctly, right? You always have that feeling in mathematics, well, how did I get it, or did I do it correctly, basically. So what you can do is, why don't we take the derivative of this function? If I take the derivative of this function, I should get this, because guess what? I did the opposite of differentiation, so if I differentiate, I should just go back to the function. So if I take the derivative of the primitive, I just get the function. That's all I'm saying, alright? So let's go ahead and do that. So what's the derivative of x to the 5 over 5 plus c? Well, the plus c disappears, right? Just gone, right? So I bring the power up to the front, and I lower the power by 1. So what's 5 minus 1? That's 4. And there's a 5 down there. 5 and 5 cancel. And I have x to the power of 4, exactly what I had up there. So whenever you take an integral, you can just go ahead and differentiate it to get the function that you had in the beginning, just to check your work. So as you can see, we found the integral of x to the 4, which was x to the 5 over 5 plus c. And if I differentiate that, I get exactly x to the 4. That's really what I wanted to stress in this video, taking anti-derivatives. So let's do one more example before I end the video. What if I had 1 over x squared? That does not look like an anti-derivative. That does not look like just a function to the power of something, right? It doesn't look like x to the power of something, like normally. So what we can write this as, if you remember from just exponent laws, I can bring this up here, can't I? Right? This is the same thing as saying that. So now I can just apply my normal integral laws, right? So x negative 2 plus 1, and then divide by negative 2 plus 1, right? So this is, what's negative 2 plus 1? Well, that's just negative 1. So x to the power of negative 1, and then negative 2 plus 1 again is negative 1. And you can leave it as that and say plus c. So the integral of that is just x power of negative 1 over negative 1. You want to be cleaner, you can always bring the x down here and just say negative 1 over x plus c. Again, that's all you have to do. You just brought the power up there, and now it looks like something we can do, right? So x n plus 1, and then divide by n plus 1. All there is to it. So hopefully this video really introduced you into antiderivatives, so the opposite of differentiating. In the future videos we'll do many more antiderivatives, and we'll start talking about the area under the curve and how we actually get to that. I hope this series will be really exciting. All this stuff is really cool to learn right after differential calculus. All this stuff is very easy to learn too if you take it right after differential calculus. What happens is that you do differential calculus, and after a long time you get into integration, and it doesn't all make sense because we haven't done differentiation in a while. So if you've done differential calculus very recently, this should all be pretty exciting to learn. So hopefully that helped, and please subscribe if you're excited about these and you enjoy my videos in general. Thank you.